Problem 30, substring with concatenation of all words. So in this problem, we are given a string, like this one, and also separately an array of strings. Now, in this array of strings, each string will be referred to as a word. That's also the name of the array, words. All of the words have the same length. So all of those strings have the same length. We are allowed to combine these words in any order we want. So we can construct a valid sentence with all of these words glued together in any order. So no spaces in the middle or anything, just foo bar or bar foo in this case, right? So if you have one of those words used multiple times, then we have to use it in the sentence exactly as many times as it's given in this array. So if it was 2 copies of foo, so foo bar and again foo, let's say, then we could construct foo foo bar or bar foo foo. But basically we have to use all of those words that are given exactly as many times as they are given in this array. And we have to come up with this valid sentence, right? Which in the problem is called a concatenated string, but I think our name sentence is better. So for any sentence that we come up with, any kind of permutation of this array, say foo bar, right? Foo bar. We have to find this foo bar, this permutation inside this bigger string. I probably shouldn't say a bigger string. We don't know how big this will be. But if we look for this foo bar inside the string, if we find it, we have to note its starting index. It's 9. So foo bar starts at index 9. No other occurrences of foo bar. But if we take bar foo, another permutation, right? Then bar foo does occur here also once, and its beginning, it occurs at position 0. So 0 and 9 are all of the occurrences of all permutations of this words array inside this target string. Excuse me. So we're going to return basically this array of every starting position of every permutation. Slightly convoluted kind of problem statement, but not too much. I mean, it's understandable, I hope. Now, this is a hard problem. So I want to try to come up with an efficient solution. So at least in terms of time complexity, we beat as many solutions as possible. So you can see there are 6,710 accepted solutions out of roughly 3 times as many, almost 2 million. So we want to try to beat as many of those 600,000 solutions as possible. Hopefully all of them, right? We'll see. Because, I mean, it's not going to be an easy job because obviously we're competing against some tough crowd here. So, but let's see what we can do. Right. So this is our brainstorming kind of environment. So I prepared these. This is our string, right? And that's our dictionary of words. Now, you might be slightly alarmed when you see that I have kind of created these mental separators here. These are not empty characters or anything. There is no character actually here. No white space characters. I've just mentally separated these chunks, and conveniently I've made them the size of each word, standard word size. So each word in our dictionary has the same size. So I've created this kind of convenient separation, which could alarm you probably. You could say, well, I mean, if it was possible to do this, then we could indeed try to come up with a very fast algorithm, an efficient algorithm to deal with this. But I mean, that's going to be misleading because, well, you could find some valid solutions here. So, for example, CDABEF, right? CDABEF. So this is a good solution. So we could return one of those starting indices, and we could find some other ones as well, as long as they start conveniently at some of those breaking points that I've prepared in my imagination, right? But you could say, but what if they start at different points? So, for example, if they start somewhere here, we won't be able to find this substring as a permutation of these words. And you would be right. But here is my counter argument. Why don't I consider different breaking points? Like, so this would be 1. So my first breaking point would be at index 0, right? But then, why don't I... Okay, just one second. So this is my first breaking point at index 0. But then I can try to do breaking point here. So that would be first breaking point, second breaking point. So our breaking points would be like this. Yes. And then I could also try to use this as a first breaking point. But I mean, this is no longer required because when we initially did the first breaking point here, it would basically produce the same breakup. So you could easily guess that how many different breaking points should I consider? How many different initial offsets before the first breaking points? So that would be the length of standard word in the dictionary. Okay, I hope that's clear. Yeah. So what I'm going to do is I'm going to go through 0, 1, and all of basically through the entire length of a standard word and consider an offset with 0 or 1 or whatever the number I'm looking at. So I'm going to ignore, for example, this 1. If I'm looking at offset 1, I'm going to ignore the first 1 characters, and then I am going to use the breaking points after every 2 characters, in the sense that 2 is the length of a standard word. Okay? So outside, I will have one big loop, which will be basically, I will have probably a variable called offset, which will be going from 0 to, so offset would be, from 0 inclusive all the way to word length exclusive. Yeah. This will be the outer loop. And inside this loop, I can pretend that my string starts at this whatever offset I've ignored. So it starts somewhere here at this offset. Okay. And it's broken neatly like this after that. And what I'm trying to say is breaking string like this, imagining that the string is kind of broken into chunks like this, should allow me to come up with a very fast algorithm. Okay? That's my claim, and also my hope, kind of, that this will be fast enough to beat as many potential solutions as possible out of those 600,000, right? 722. All right. So what we're going to do inside this loop. So inside this loop, we have our string kind of with some offset, broken conveniently into these chunks, word size chunks. or broken into words, we could say. Now, here's what I'm going to do. I'm going to start looking at ranges. Well, initially, I would be looking at the empty range at the very beginning, right? But at some point, let's say I'm looking at left and right, which identify a range. So right is an exclusive end. When left is the first index of the first character that I'm including in my range, right is the index of the first character that I'm excluding from my range. Okay, so that's left and right. Inclusive start, exclusive end. All right, so that's my range. Now let's say I have somehow identified, checked this and identified that all of these words, I'm just looking at these chunks, word size bits, right? I'm not looking at any of these kind of weird overlapping things here. Just all of those, let's say, normal chunks like this. And I'm allowed to do this because I'm kind of imagining that within that larger loop, as we said, we can do this. So let's say all of these occur a correct number of times, in the sense that, so for example, EF does not exceed the number of EFs that we actually are given. So currently we only have one EF, so it should be maximum one EF or less. Let's say, fine, 0. AB, we have one AB, so the number of times AB occurs in this range should not exceed this one, etc. Right? For example, if CD, if we had more CDs available in our words array, let's say we had 3 of them, then this range should not contain more than 3 CDs. Okay? It may not contain all 3 because the problem requires basically that a valid sentence should contain all of the words, all of the occurrences of all of the words. But in here, while I'm going through this, I would say my range is still fine. If it's still, I will say this range is still fine if it does not contain anything extra. It may be missing bits yet. I'm not going to complain about this, but as long as it does not contain anything extra, any garbage that is not here at all, or if, say, this word is here, but I shouldn't be using it more times than available. In this case, I would say my string is fine. My range that I'm looking at, this range here, let me get rid of some of this. So my range is okay. And if my range is okay, I am going to add one more word to the right. So I'm going to expand my range, move R to point to this element. But if my range is not okay, then I'm going to start removing elements from the left, removing words from the left, until my range becomes okay. And even if I have to completely reduce this range to an empty string, I'll keep removing those words until it does not contain anything extra. Okay? I can always do that. So to kind of go through this, you can notice that basically when I expand the range, the only way I'm going to expand it is by adding a word to the right. Okay? So the only way that new words going to come into our range will be to the right. And I can slightly rephrase my algorithm. So every time I add a word, I can instantly, afterwards, I can try to remove as many words from the left that will make it so that it's no longer contains anything extra. Okay, so CD in this case, it occurs here, so once, so it will remain equal to the CD. Yeah, because this was an extra CD that I have removed. So kind of you can see what's going on. You can see where this algorithm is going. So inside this big loop, inside the inner nested loop. So when I do each iteration, I will start with my string always being okay, in the sense that it does not contain anything extra. So if it does not contain anything extra in the beginning of each iteration of this inner loop, then I will just add one more word to the right, and that could potentially somewhere here in the middle of my iteration, that could potentially break this thing that everything's okay. But right afterwards, I am going to start to remove words from the left and I'm going to keep doing it until everything becomes okay again. So that I exit the iteration with everything being okay, with my substring being fine. And right before I exit the iteration, I'm just going to say, well, I know that this substring is okay, so it does not contain anything extra. But does it contain enough stuff? Does it contain all the words? And I'll just check the length of this thing. If the length of my substring is the length of this entire array joined together, that means, well, that means my starting point is a good starting point, which means this is the starting point of the actual permutation that the problem requires me to find. So I can push the starting point into my answers array. I think that makes sense, right? Now, if you want a proof that this will work, maybe a mathematical proof that this will work, it's not too hard to notice, to kind of prove that this will work. You can prove, so I'm probably not going to do a full proof here, but roughly what you will say is left will always be less than or equal to right. This could be your first lemma that you will prove. And you can see this is easy to prove because you will see how you're gonna be incrementing right or left. So it does not matter when we increment right. So when we add more words, that is not dangerous because, I mean, by increasing R, there is no danger of breaking this inequality, which initially is obviously correct because we're going to start both left and right equal to our offset, right? 0 or whatever offset we're starting from, both will be equal to that offset. I think we mentioned that, no? So initially, this will be fine. So adding new words to the right is not going to break this inequality. But when we remove things, again, that's not going to break this inequality because at the worst case, if we add some garbage here, for example, some xz, which is not here, then we're going to end up actually L being equal to R after we remove pretty much everything, including this word as well. And that's when we're going to stop removing because at that point, our range will be reduced to an empty range, the substring, empty substring. So then we're going to re-enter the loop and increment R. So this is kind of easy to prove. And after that, you can see that if you have any of these valid kind of substrings here that actually equals to some permutation of our array, you will see that therefore when R finally enters this, and we'll make sure that R will go through the entire kind of R should go through the entire the string. When R finally enters, L must be somewhere behind, right? Because just before R entered, they must have been the L could not have been already here before R. So when R enters, so L is here somewhere. somewhere to the left. So I will show you that R will be the first to enter here. Then R cannot go beyond this point until L also comes in. So R cannot go beyond this point until L also comes in. And this is easy to see because if L hasn't come in yet, then what will happen? You cannot, so you cannot increment R beyond this point, right? Why? Because if this contains every word from here, exactly the maximum number of times, then because L is not here, it's somewhere at the beginning of the previous word. So what are all of these other words? That means this thing is not okay. It contains some extra stuff, right? It cannot contain nothing extra. So if it contains extra, we're going to keep removing this, and we're going to keep moving L until L comes here. And also I'm going to prove that, so once L does come in, it cannot budge from the first word. So it cannot go to the next word until R gets here. Okay? And that's also easy to prove because let's say if L tries to budge, that means we are removing some of these extra characters. Something is extra. But R is not pointing beyond this. R can be, we said, R, let's say R hasn't yet reached this. Right? R hasn't reached this. If R hasn't reached this, we cannot have any extra characters because L is inside this. L is inside this, this little permutation substring. And if R hasn't reached this place, then nothing here could be extra. Even if R is actually right here, even now, still nothing extra can be found in the string. Because this is, as we said, as we presupposed, this is an actual one of those permutations. So if this is the case, R should keep increasing, not L. Okay, I think I said I was not going to prove it, but I did prove it. This is a proof. Okay, now we should start implementing this thing. Okay. All right, let's start implementing it. So here is the function, but where is the function? Okay, so this function, I'm going to copy it to a different editor, and this is typescriptlong.org, which has a playground. So this is the playground of typescript.org. Slightly better editor. So now, what did we say? How are we going to do it? So first of all, I kept mentioning that at every point I was going to check if we have everything in the correct number of occurrences, right? So I need to know what the correct number of occurrences is in this array. How many times each word occurs here? I need to know that. And let's calculate that first. So what should we do? Let's give this word count. Let's call this word count. And this would be new map of type mapping words to numbers. Words to count, their count. So string to number. And we could initialize this, we could populate this in multiple different ways. But what I'm going to do is, let's say, for constant word of words, I mean these words, right? So, whoops. For each word, what we're going to do is we're going to say, what is the existing count of these words? So that would be word count, get word. Yeah. But this could be undefined. If this is the first time we find this word. It's undefined, so we're going to change undefined to 0 and then add 1. So this is the previous count of this word. Previous count that how many times we've seen this so far inside this array. Previous count, add 1 to account this particular occurrence. Now we should write this back to word count for this word, right? And we're going to do this word count set word to this number, okay? So that should create word count. The next bit we said we're going to do is, we said we're going to create, where's my pen? We're going to create this outside loop, which will kind of move offset through 0 to word length. So let's do that. For let offset equals 0, offset is less than, strictly less than word length, which we have to create. We don't have word length, plus offset. Okay, now word length, we can create word length here. Okay, let's create it. No, you know what? We need word length. We don't need word lengths there, so I'm going to create it. Constant word length equals what? Words 0 dot length, right? But words 0, does word 0 exist? Yes, I'm sure it does. If we look at the constraints, yep. So there is at least one word and at least one character inside the string S. But it's not too difficult. Why don't we just protect ourselves from some weird... I mean, we don't need this protection for this problem, but let's still do it. If words length does not exist, so if no words length or no S length, then return empty string, empty array, which only makes sense. Good. Now we can say word length equals this. All right. So as soon as we go inside this loop, now as we said, we are inside this loop where we can, where's my pen? Here. So we can think of our array to be broken like this into bits. So whatever the offset, so let's say this is our offset. So everything else we ignore. Offset starts here, and then everything is broken into convenient chunks size of a standard word. Okay? That's what we're going to do. So we are going to start with let left equals offset and right also equals offset. So we're going to start with an empty, we're going to start at this offset, we're going to start at an empty range initially, so empty substring. It has nothing inside. We're going to look at empty substring first. And now we're going to try to add something to it. Right? How are we going to try to add something to it? Inside this while, we'll keep adding words to the substring. How? So right plus word length must be less or equal to S length. Yeah? So in order for us to be able to add another word, see what's going to happen here? So imagine any range, any substring that we're looking at, right? So this is like so. So left and right, remember, right is pointing. It's an exclusive AND. First character that we don't need. So if I add word length, right would be pointing here. Okay? And I'm allowed, excuse me, I'm allowed to point all the way to here. This is, let's say, end of string character. Let's say there is a special character. Let's imagine a special character, end of string. So I'm allowed to go all the way including to this, because my R is actually exclusive. So this is correct. This is correct. Yeah. But also, I mean, also if left at some point gets too close to the end of here, and there is not enough characters simply left to build a string like this, then also there is no point in continuing. So I would say if left plus sentence length, I don't have sentence length. So we have word length. Why don't I create constant sentence length? And that would be word length multiplied by word count, words length. So this is the number of words in the array, and this is the length of each word. Or the first word, let's say, but I mean, we know that they're all equal size. Right, so what did I do here? So left plus sentence length should also be less than or equal to s length. Why like this? I mean, imagine, let's say a simple situation. Imagine we have just a single word made of a single letter. Let's say A. Undefined article A is the entire dictionary. And S is also string with a single letter. In that case, this is 1. This is also 1. So for what values of length will be allowed inside this loop? 0, right? Left is 0. So 0 plus 1 is less than or equal to 1, which is precisely correct. We should be allowed in if left is 0, but not if left becomes a larger number like 1. There is no point in trying this anymore. So this is our loop. What are we going to do inside the loop? So inside the loop, we're going to add, excuse me, so we're going to add a new word, we said, right? So right is pointing here. So right is pointing here. And we need to incorporate this new word. What does that mean? So we need this new word. Let's find that new word. So that new word, it will be constant word equals s substring. Starting point would be right. And then remember, because right, we haven't updated right yet. Right is still pointing to the first character we haven't used. So this will be the first character of the next word, right? And then all the way up to right word length. Why? Because right, if you take right and add word length, then you're going to move to this. Yeah, correct. But then this would be the first word the first character that you don't need. And that's precisely how substring works. For substring, this substring, second parameter is exclusive end. Okay, that's beautiful. So now I'm going to update right. Right plus equals word length. Okay, so I've updated right. So after this point, my loop is kind of fine. Because this, in some sense, you can consider these two things as part of this header of the loop. These two commands are kind of belong together here. So somebody might try to rewrite this while into some sort of for loop where these two things are also part of here, which will just look horrible probably, but in terms of meaning would be even better. But I'm not going to try it. I'm also not going to optimize. See, right plus word length is calculated 3 times on these 3 lines, and there are some temptations to optimize it something like this, and even worse. But I'm not gonna do this either. Okay, so now that we did this, we added. So remember what we're doing. So we said inside every iteration of this inner loop, we're gonna start. This iteration will start with string with this range being okay. Then we're potentially gonna temporarily upset that by adding one more word, which we already did. But now we're gonna start removing as many words from the left as necessary so that we we may have temporarily upset this balance, and we have to restore the balance now. Okay, so we've temporarily upset the balance here by adding a new word. So we need to restore the balance. How do we restore the balance? So we need a couple of things here. So first thing we need is this word that we've just added. How many times can we use that word? And this was counted here inside word count. Remember, word count, we just took all available words in the dictionary, in this array, and we count how many times each word occurs. So now we have to say constant max use of this word. Let's call it max W use. It's not nice. Max use equals word count get word, right? Now, I don't want undefined. Let's turn it into 0. If it's undefined, we'll turn it into 0. Yeah, because this word could be an unknown word, invalid word, not from the dictionary. So this would be undefined, and we're going to turn it into 0. Okay, that's the maximum use. But what is the current use? Well, current use, instead of counting current use every time, right? Instead of going through this thing, yeah, and counting the use of this word, which would be inefficient in terms of time, let's use a little bit of extra memory and try to optimize that, because we said I want to build something very fast. I don't care about memory that much as long as memory usage is reasonable, but I don't want to really optimize for it. I want to optimize for speed. So I'm going to do something like create another map and say use count. And that will be new map. For each word, it will be the number of times this was used in this range, in the current range that we're examining. So max use is this. You know what? Let me do this before max use. First of all, let's find out how many times this was used. I know it's going to be not going to be. Okay, let's write it as a constant. Constant, what should I call it? Constant word use of this word. So word use. So how many times this word was used, including this occurrence here. And this was used by, well, I just created this map, which I'm going to maintain, I promise. So this one, get value for this word. If it's 0, then just add 1, because we just need parentheses. So here's what I'm doing. Get the current use, whatever the use we said. So I'm going to keep maintaining this use count. So I should be able to retrieve this word, its count from here. If it was never used here, then I'll just turn it into 0. Add 1, so this will be word use. But because I said I'm going to maintain it, I have to write this back into use count. So use count set word to word use. So normally these two commands could be just written as a single command by taking this and just pasting this here. But I'm not going to do this because I need this variable. Yeah, I don't want to query this map multiple times. I'm going to need this variable. Why? Because we're going to actually bring this word use down to max use. If word use is over max use, we said, we're going to try to bring this word use down to max use. Remember? So we said, after we add a new word, we could potentially temporarily upset the balance, but we're going to immediately try to remove as many words from the left as required so that the balance is restored. So that's what we're going to do now. So now we're going to restore the balance. No, you know what? I'm going to move max use to the top. just so that these two lines are next to each other. And I also want this line to be right after words used, because these two are logically related, and these two are kind of logically related, and also they kind of look similar. I think this is, I just like it like that. Now I'm ready to enter a while loop. And we said while in the sense that while word use is strictly greater than max use, then this is not okay. If word use, the actual number that we've used this word, is more than allowed max use, if it's strictly more than that, then we have a problem. So we need to try to reduce, we need to remove words from the left. So let's say word to be deleted would be what? Word to be deleted would be this one. So left, starting from the left index, right? So S substring from left, and then left plus word length. Okay, so that's the word to be deleted. This one, wdel. Now, if this word to be deleted exactly the same as the word we've just added on the other end, then then word use should be decremented, right? Oh, word use is constant. We need to make it let. Okay, so word use needs to be decremented, right? Because here we're going to remove a word, this word, and this word is exactly the same that the one that we just added from the other end, and this is how many times we said it was used. So we need this value to be decremented, right? And then we also need to, well, because we're going to remove this word, we're also going to update use count, because I said I'm going to maintain it, right? So here is how I'm matching this promise that I'm going to maintain use count, but also here, right? So use count set word, not word, wdel to what? Use count get wdel -1. But TypeScript doesn't understand that this will actually be number, and positive at that, positive number. So I can't tell it, because I know this cannot be undefined, and this cannot be 0, because I'm removing a word, this wdel. And if I'm removing the word, then this word must be there, right? So its count cannot be undefined or 0. Okay, so this is good. And now I can update left plus equal word length, right? So I think together these commands are what we need in terms of removing words from the left. Yeah, that's, remember what, so every time we remove words from the left, we identify the word that needs to be removed. If it's the same word as the one that's being added, then we need to update word use. And also we need to update the count of this word inside use count. Now notice this one is kind of, this word use is not even necessary here, because this word use is basically a copy of use count get word. Yeah, use count get word. It's this one. But because I do not want to keep looking this up every time I kind of check this condition, because it's probably kind of costly, I think. On average, it's 0.1, right? But it could be potentially costly. So that's the only reason why I've introduced this variable, word use, to avoid writing an expression like this here. Okay. All right, so I've done this. So I've removed words from the left. I've removed words from the left. And now, basically, what I've done is I've restored this balance as promised. Yeah, this balance is now restored. This means our loop is pretty much over, except for one thing. We should say here, well, now my string is okay. We've made it larger initially, and then potentially removed any number of words, as many as necessary, to make it okay again. So it doesn't contain anything extra. But does it contain everything? If it contains everything, then this starting position left, wherever it points to, the starting position left is acceptable. We need to push it into the answers. Okay? So if it equals to, so if right minus left, that would be the length of entire substring, because we are using exclusive AND, so right minus left. Then if it equals to sentence length, right? If it equals to sentence length, that means nothing was used, nothing extra was used. But if it's used equals to everything, then we've used everything. That means we need some sort of array. I'm going to define it here. Constant answers or starts, substring starts, permutation starts. Let's call it p starts, permutation starts. Not a great name. Number array, and it's initially empty. So if this is true, then p starts push left. Okay? And now we're finally ready to get rid of these red squiggles here by doing what? By returning p starts. Okay? Hopefully this is, everything's correct. Hopefully I haven't messed things up here. Copy. I'm going to paste it to, I'm going to paste it to here. Whoa. Let's fold it. No, maybe not fold it. You know what? Make it smaller a little bit. And submit it to the pretests. Okay, everything's good. The pretests are fine. Let's now try the actual test, the full suite of tests. Let's see what happens. What happened? Did I not submit it? Okay, so we beat 78%. Not great. Not great if we beat just 78%. Well, in terms of memory, we did much better, but okay, Okay, what can I do here? Maybe optimize it a little bit more. So here is what I might be able to do. Let's clean this up a little. So let's say after I add one more word, just one more second, let me clean this up. So when we add this word, now here's this case. This word could have 0 occurrences in this array. Okay. Now this is kind of a special case. Okay. If it has 0 occurrences of this array, what will happen is finally we're going to get rid of everything, remember, and left and right will end up pointing both here. So we should short circuit that. Not sure if this will actually be very helpful, but let's see. After I calculate max use, right? I calculated max use. Let's say if no max use is allowed, so there is no max use, then what should I do? So left should equal right. Yeah. Why? Because, right is already pointing here. So remember, we added this word. Right is already pointing outside. So right is here. I can just move left to also point there. Now we need to reset use count. Remember, I promised that I would maintain it. So every time I do something like this, I have to remember that I have to maintain use count by clearing it, right? I should clear it and then continue. And by continue, basically, we're going to re-enter this loop immediately, right? So left and right are equal, just like the way we're going to enter this loop for the first time. So left and right will be equal. So we're going to re-enter this loop. Use count is clean. And then we already know this. So we'll try to add one more word. Yeah. Okay. So why don't I copy this again back to here? First of all, let's do pre-tests again one more time, just to be on the safe side. Okay. So I'm going to now submit it. Okay, I've submitted. Let's see if this gives us, wow, this is considerable improvement. I mean, 97%, we beat 97% in terms of speed and 95% in terms of memory, which is decent, I would say, considering, remember, we have 600,000 solutions, so 1.8 million attempts. Obviously, in terms of speed, we beat these, but the rest, about 1,200, so 1,200,000, well, they didn't make it, but these ones that were actually submitted 600,000 solutions, we didn't beat all of them. We just beat 97 point. Okay, so there are some solutions that are faster than ours, or at least as fast as ours, or maybe even faster. But for TypeScript, I think this is a decent result. Okay, great. That was nice.